Hey, we're going to look at properties of fluids a little bit more, and this time what I want to do is talk about the atmosphere. Now, the atmosphere, if you look at the world, right, we have let's say this is the land right here. Okay, that's bad, but anyways, the idea is that we have a sphere of gas around the Earth, right? And that sphere of gas goes up, about 20 miles or so, and it weighs something. Like, it has mass, because gas, remember, is made of particles, right? And so these little particles are moving around, and on any surface that is here, let's say that this is sea level right here, it's going to have the force of all these miles and miles of gas smacking down on it. And how much force is that? Remember, we talked about in the last video how a Pascal is a Newton of force on a square meter. So if you think about a square meter, how many newtons of force would, if you could take that square meter and just take that 1 square meter all the way up to space, how much force would those particles just in that square meter all the way up have on that surface? It turns out they would have 101,325 newtons of force on that square meter, right? So that's amazing. Now, that is a force to be reckoned with. And later on, we'll learn how this particular force right here is enough to bring a 1,000,000-pound airplane up into the sky. I mean, just incredible amounts of weight can be taken up into the sky, and actually just using this atmospheric pressure right here. So we have this on us, and now this is important. You'd think, wow, that's a lot of force. 101,000 newtons is a lot of force, but we're grateful for it. It actually keeps the gases in our blood from turning into gases, and so we have liquid blood. If you were to go up and not have that force, you would have gas blood, and then you would be very much dead. And we'll talk about some of that later as we go through and get more and more into the properties of fluids. But right now, I just want to look at the atmosphere and the atmospheric pressure, and look at this. Now, there's other places you could go. You could have more pressure, like, for example, if you were at the center of the sun and had the gases, which is mostly just hydrogen gas or just hydrogen above you. And think about hydrogen as the lightest element, but still at the center of the sun, the force of all of that mass on top of you would actually be 3 times 10 to the 16th newtons per square meter. Wow. So just imagine the crushing amount of force that there is right there. Venus has a atmosphere which is way thicker and more dense than ours. So at the surface of Venus, not Wiener, the pressure would actually crush you, would actually destroy you, and has destroyed many of the probes that we've sent to explore the surface. Let's go ahead and look at an example right here of something that sort of happens when atmospheric pressure changes. For example, if you have a tornado, here we are, there's a tornado. What happens in the tornado is the gases start moving really, really fast. And when these gases start moving really, really fast, it takes less of them to sort of equal out the surroundings, and the velocity increases. And one thing that we're going to learn later is that when the velocity of a fluid increases, the pressure decreases. Velocity increases equals pressure decrease. So one of the most damaging things about a tornado is actually that the pressure is lower. It's a low pressure area, a super low pressure area. In fact, about 15% lower than the area around it. So if you've got a tornado and it goes over a house, this is a house, here's the chimney, okay? One of the things that actually happens as a tornado goes near a house is the windows will actually explode out, not in. And so why is that? Could we figure out what is accounting for that? And it's a pressure difference. Okay, so if you look at the pressure, let's say we've got a window that is 195 centimeters by let's see, what did I write down here? By 91 centimeters, right? So say it's your window right there. Why will the window explode out? Well, if I take this, remember pressure equals force divided by surface area, right? And so what is the force of the atmosphere? Well, we know that the force of the atmosphere per meter is 101,000 kilopascals. It happens to be 10 newtons per square centimeter. Okay, so if we were to take that 10 newtons per square centimeter, and we were to figure out, okay, here's our surface area right here. If we were to multiply that times our surface area, let's see, and so this multiplied by this is going to be 17,745, and we multiply that times 10. Then we're going to get the actual amount of pressure that the windows normally have on them. Okay. Now, if I was to go ahead and I was to lower the pressure 15%, well, now when the tornado hits it, it's going to be 8.5 newtons. So I have 8.5 newtons per centimeter squared, right? Multiply that times the surface area, right? Now we're going to have a difference here of 8.5 and 10. And so that, if we went ahead and subtracted that, that's going to give us a difference of 26,617.5 newtons. Oops, I said point N. 0.5 newtons. And so where's that pressure? Well, on the inside, it was still the regular old atmospheric pressure. But when the tornado came over it, now on the outside, the pressure is 15% less. And so the difference in pressure is pushing from the inside out, because now there's more pressure on the inside than there is on the outside. All of a sudden, the force on the outside was lowered by 15%. And this accounts for 26,000 newtons that's going to push from the inside out. And it's basically going to blow these windows out. And so that's a net difference. So that's why a tornado causes windows to bust out of a house like that. So atmospheric pressure, especially if it's messed with, is a force to be reckoned with. So in some later videos, we're going to show how does this keep your blood from boiling and how does this make airplanes fly.